Hello and welcome back to statics. In this example, we're going to be looking at problem 5.23. You can see the diagram here at the top of page 93, but the description is down here at the bottom. So let's read through the description and then go back and take a look at the diagram. It says the boom OA supports a load of 10 kilonewtons as shown. The uniform boom weighs 2 kilonewtons. Find the reactions at O and the tension T in the lifting cable. So let's go back and take a look at this. Right? And if you take a look, we have a boom here, right? It has a 10 kilonewton load at the top. Its own weight is 2 kilonewtons. It's symmetric, so it's right in the middle, 6 meters and 6 meters. It's at an angle of 60 degrees, and there is a tension cable coming down here that's at an angle of 30 degrees. So I'm not going to pause the video and set this up in our homework format. I recommend you do the same, and we'll continue on. Okay, again, it's our fifth example in Unit 5 on rigid body equilibrium for EGR 251. If we take a look at the problem, we're doing 5.23, given the diagram. Here it is shown. We have this boom. It has a weight hanging from the end of it. It has its own weight right here in the middle, 6 meters up or 6 meters down, depending on how you look at it. It's at an angle of 60 degrees, and the entire structure is being held up by a tension cable, which is at 30 degrees. Right? In addition, we know the weights, 10 kilonewtons at 1 and 2 kilonewtons at 2. That's the weight of the truss itself. They want us to find the reactions at O and the tension in T. Right? This is the lifting cable. We're going to assume it's a rigid body, so there's no deformation, but we don't have to assume it's weightless. They give us that. So let's start out by doing a free body diagram. And again, we can always simplify our free body diagrams. That worked kind of nicely in this one. I'm just going to simplify this beam as a line. And if you take a look, we have our weight. Right? We'll call this weight 1. Right down the middle, we have another weight, scaling a little smaller because it is smaller, and we have our tension at T that we know is at 30 degrees, right? And then down here at O, keep in mind it's a pin joint, so we're going to have both a Y component and an X component. And again, we're trying to solve these, so if we take a look, I know this is probably acting upwards. All of these are acting downwards, so it's a pretty good indication it's acting upwards. But what about our X component? Well, the fact is T is pulling to the right, so it's distinctly possible, very likely, that O sub X is going to act to the left. Now, if you recall, I've told you all along, you can always assume it's positive, and if it comes out negative in the end, that's just fine. So how to go about solving these problems? Well, we do a couple different things. We obviously can use forces in the X and forces in the Y. But if we take a look at that, let's say, for example, we do forces in the X direction. Well, T is unknown and O sub X is unknown, so you can have two unknowns. If you do forces in the Y direction, T is unknown and O sub Y is unknown. So again, two unknowns. So let's try to figure out a spot where we can eliminate at least one of the unknowns. And the simplest place to do that is point O, right? If we take a look at point O, we're going to have the weights and we're going to have the tension, but we're not going to have any of the forces at O. So summing moments about point O will solve at least part of our problem. So let's set up and show what forces we have about point O. Or forces that cause moments about point O. We know they're going to be equal to 0. And so what do we got? Well, we have W1, we have W2, and we have T. Right? Now here's where the problem lies. The fact is, if we're going to take a look at this, we need to come up with the various distances, right? And if you recall, this is 6 meters, this is 6 meters, and this is 60 degrees. So the good news with these is we can easily find these. If you think about it, this is the hypotenuse, this side is the adjacent side, and in terms of your SOHCAHTOA, that's cosine. So we know that this distance, for example, is going to be 6 meters cosine 60. So let's put that in our calculator. 6 times cosine 60. Right? That gives us 3. If you recall, cosine of 60 is 0.5. This other one is going to be 6 and 6, or 12 times the cosine of 60. And I'll put it in, but again, I know that the cosine of 60 is 0.5. So that distance is going to be 6. So for W1 and W2, we can have W1 is going to be 6 meters. W2 is going to be 3 meters. Right? Now, T is a little bit more complicated. So how could you possibly do that? Well, you could come up with components. Or if you think about this, fact is, you could also determine the perpendicular distance. Right? Because if you think that's 30 degrees, the alternate side in here, right? So this total one has to be 60. So this has to be 30 degrees. And this has to be 60 degrees down here. Right? Because 30, 60, and 90 is going to add up to 180. So what is that distance right there? Well, again, this 12 is the hypotenuse, right? And 60, this is the adjacent side, right? So if we wanted to determine that, we could go through and say our hypotenuse times this adjacent side, right? And so again, it's going to be 12 times cosine 60. And it's going to give us 6 meters. Right? Now, you can do it with a tangent, with the horizontal and vertical components, but the fact is, this allows us to get right to the problem without having to worry about components. And if you take a look at this, this we know, this is our only unknown. So last thing we need to do is talk about what moments and what they cause. If we take a look at this, W2 clearly causes a counterclockwise rotation, right? W1 also a counterclockwise rotation, but T causes a clockwise rotation. So that's going to be negative, that's going to be positive, that's going to be positive. They all have to add up to 0. So we can manipulate it around. 6T is going to be equal to 6 times W1 plus 3 times W2, which equals 6 times 10. That's 6 meters times 10 kilonewtons, plus 3 meters times 2 kilonewtons. All of this is going to be divided by 6 meters, and that'll give us T. So let's just plug that in. We probably could do it in our head. 6 times 10 plus, what was it, 3 times 2. All right, that's going to give us 66 divided by 6. Going to give us 11. So T in this case is equal to 11 kilonewtons. Now that we know T, we go back and try to find some other moments. But if you think about it, there's no place really convenient where O sub y and O sub x disappears and T disappears. So probably better off at this point to go back to using forces in the x and y, since we now know what T is and we know, of course, the angle. So if we go to that, sum of forces in the x, we know they got to be equal to 0. But what forces do we have acting in x? Well, we have T, right? But not all of T. Right? Keep in mind just part of T. In this case, it's going to be T, and of course, this is the our case here. We have our adjacent side, so this is going to be T cosine 30 degrees. That's going to give us our x component. That's acting in the positive direction, minus O sub x. Right? And so all that means is that O sub x is going to be equal to T cosine 30 degrees, which is equal to 11 kilonewtons times the cosine of 30 degrees. If we put that in, 11 times cosine 30 degrees, right? It's going to give us 9.526, or which equals 9.53 when we round it. And again, that's kilonewtons. Right? If you recall, we have it in the negative direction, so we probably should put that in there, and don't forget to leave that out. That's going to be equal O sub x. Right? And now if we want to do forces in the y direction, they have to equal 0. Well, we have T sine theta, in this case sine 30 degrees, right? Because it has, and of course this is negative because it's acting down. We have minus W1 and minus W2 and plus O sub y. O sub y is really the only force that's acting upwards. So if we manipulate that around, we move O sub y, actually move all the other things to the other side. So we have O sub y on this side, right? And so because we're moving these to the other side, all the negative signs go away. So we have T, which is our 11 kilonewtons times the sine of 30 degrees minus W1, which is again 10 kilonewtons and minus 2 kilonewtons. Oh, I'm sorry. Since we're moving to the other side, this would be plus 10 kilonewtons and plus 2 kilonewtons. So we go through and do the math. Right. We have 11 times the sine of, what do we say, 30. Close that. Plus 10 plus 2. And that comes out to be equal to 17.5. So there we go. O sub y equals 17.5, and again that's kilonewtons, and it is upwards, so it's positive. As usual, if you have any questions about any of these problems, definitely do not hesitate to get in touch with me or take a look at the video again. Be happy to help you out with that.